Hello students, welcome back. Are you having trouble visualizing reaction pathways and predicting final products? Don't worry. At OrganiChemVerse, we break down complex reactions step by step to help you find the right mechanism and determine the final product with confidence. So let's dive right in. Whenever you look at the reactions, first try to identify what are the reactants and the reaction conditions given. For example, for the given reaction, the reactant molecule here is a cyclic ester, nothing but it's a lactone molecule, a 5-membered lactone molecule. What about this? It's a methyl phenol, nothing but it's orthocresol, and it is treated with aluminum chloride under heating condition. Whenever you see aluminum chloride and an aromatic molecule, remember this could be either Friedel-Craft alkylation or acylation. Then how do you decide whether it is alkylation or acylation? By looking at the reaction conditions here. If it is alkyl halide, then it's going to be alkylation. If it is an ester, anhydride or acid chloride, then it is Friedel-Craft acylation. And also you can check the product from the options given here. If the product is ketone, then we consider it as a Friedel-Craft acylation. So in this case, definitely it is Friedel-Craft acylation. With this much information, we can start predicting what will be the product. So it's going to be a cyclic ketone, but look at the options, all of them are cyclic ketone. So which one is the right product? For that, you should know the mechanism of the reactions. The first step in the reaction mechanism is the reaction between the catalyst and the ester molecule. Of course, the catalyst will be regenerated at the end of the reaction, but the first reaction is going to happen between the ester and the aluminum chloride. Aluminum chloride is a Lewis acid. It is ready to accept the electrons. From where it will accept the electron? Look at this. The lone pair of electrons when given to this carboxyl group, the carboxyl group will give the electrons to the aluminum chloride. So we are going to get a complex structure like this. You see, there is a bond between oxygen and aluminum, right? So you can write like this OAlCl3. Now it is tetravalent, therefore, then there is a negative charge. Where should be the positive charge? The positive charge should be on the oxygen. Why so? Because this is a neutral molecule, this is a neutral molecule, but the moment aluminum becomes tetravalent, there is a negative charge. If there is a negative charge, there has to be a positive charge in the molecule so that the overall charge on this species will be 0. And look at this, oxygen is becoming trivalent. Whenever oxygen is having 3 bonds, there has to be a positive charge. Now, can we have oxygen as a positive charge for longer time? No, because it is not stable. Now, this is the one which should react with our orthocresol molecule. Orthocresol is orthomethyl phenol. So both of them are electron donating groups. The hydroxyl group is electron donating because of its plus R. It donates lone pair. That's why it will be ortho para directing. What about the methyl? It donates electron through inductive effect and hyperconjugation. But which one always predominates? The resonance predominates over inductive effect and hyperconjugation. Remember this. Therefore, with respect to hydroxyl group only, the substitution at the benzene ring will take place. So the next step is electrophilic substitution reaction. The incoming group should attack the benzene ring, but what is the position is decided by the hydroxyl group. One of the ortho positions is already blocked here, right, because of the methyl. Therefore, the incoming group should go to the para position. This is very crucial to identify what will be the product. So this is the carbon where the electrophilic substitution will take place and how it happens. So you can observe here carefully. This is a complex form and at para position, it will attack this so that this bond will break away. This bond is highly polar. So what happens here? This bond will break and both the electrons are given to the oxygen. At the same time, it is attacking this particular carbon. So what will be the product we are going to get? You see the hydroxyl and methyl groups are as it is. And here at this position, Whatever the hydrogen is there, it will get substituted by this. We can write that in one step only. And then CH2, CH2, CH2. Write 3 CH2 groups. So CH2, CH2, CH2. And what happens to this one? It will remain as OlCl3 like this. Now you look at the products. We have to get ketone, right? So where the ketone will attack, on this position or this position. That is also important. And how many membered ring? Check that also. See, we have how many carbons now? 1, 2, 3, 4 and 2 carbons from the benzene ring. So we have to get 6 membered ring. So you can rule out option 4 and 1 because we have 5 membered ring here, right? That's why you can eliminate these two options. It could be either 2 or 3. How to decide? Because look at this hydroxyl group. With respect to this is at meta position. Here with hydroxyl, with respect to this is at the para position. That's why we have to carefully choose the product now. Because we have a methyl group which is ortho para directing. Look at this. This is ortho and this is para for this. What about the hydroxyl group? It is para and ortho. This ortho is already blocked. Can this go to this position? Not possible, right? Because it's far away. So it has to go either here or here only. So according to this methyl group, it's better to go to this para position because there is a steric hindrance over here. Therefore, what happens now? It will attack over here and this bond will get cleaved. And what product are we going to get? Depending on the arrows we have used, you can predict the product. So methyl is here, form the ring over here like this. Okay, so to this position only, the ketone must be attached like this. With respect to hydroxyl, you see ortho, meta. Meta position, it should be there. And where do we have it? In option 3. Therefore, the final answer is 3. If you want, you can compare with the methyl also. For methyl, it has to be para. So this is our methyl group. So this is, you can see here, ortho, meta, para. Ortho, meta, para. We are talking about the ketone, right? The ketone should be para to the methyl. So it is para to the methyl. Hence, the final answer is as shown in option 3. Students, what did we do? First, we have generated an electrophile by reacting the lactone with the aluminium chloride. And then, based on the methyl, which is ortho para directing, ortho here, it's already blocked. Here, there is a steric hindrance. So, the cyclization happens at the para position. So, the ketone must be para to the methyl. That is what we have in option 3. I hope I made this concept clear to you. And if you still have any confusion with respect to this or any other question, you can ask your questions in the comment section. And don't forget to like, share and subscribe my channel. Thank you.